Hi, my name is Leanne, and today I'll be talking about a phosphorylation-only bistable toggle switch system. So to understand the motivation behind this project, I'm going to be explaining some examples of oscillations in biology. For instance, calcium oscillations, which is shown in the figure here. To give you an understanding of the prevalence of calcium oscillations, they occur in muscle contraction, cellular division, and apoptosis, and obviously those are very common processes. Another example of oscillations in biology or hormone concentration. An example is insulin and glucagon, which occurs in all of our bodies and regulates blood sugar levels. So in order to accurately test and manipulate systems like these, we first need to correctly simulate these environments of oscillating factors. And shown here is a general idea of a toggle switch, and there's oscillations between two states, and these oscillations can be easily controlled through outside manipulation. But what would the setup look like? And that's what I'll be going over. So some previous work that's already been done on toggle switches include one that's been designed in E. coli. And the main thing to note about this work is that it has nearly ideal switching threshold. We will explore a different design involving phosphorylation as a method for toggling. For one of the states, it's going to be run by the GFI1 and the RunX2 promoter. So the GFI1 here is shown as a repressor. When it's dephosphorylated, it binds to the RunX2 promoter. With the introduction of Aurora A kinase, that will phosphorylate GFI1 and inactivate it so that it won't be able to bind to the promoter and transcription can continue. The next state will be governed by the MyB15 and the CBF3 promoter. It works in a very similar fashion as MyB15. When it is dephosphorylated, it binds to the promoter and inactivates it. However, when kinase is present, it will be phosphorylated and then it won't be able to bind anymore. And so my hypothesis is that this proposed system, shown here, will form a toggle switch. The system in yellow represents state A and the system in blue represents state B. They work to inhibit each other and indirectly promote their own production. With outside manipulation, we can control which state to favor. For simplicity, we will only be measuring repressor levels since they parallel levels for each desired protein. So shown here are the parameters that we'll be taking a look at. Aurora A kinase and MAP kinase 6 are not given initial concentrations because that's the input we'll be manipulating. The promoters RunX2 and CBF3 have been given an arbitrary value of 1 nanomolar. And this concentration depends on the amount of plasma transfected and taken up by the cells and can easily be changed. Shown here are the rate constants, and we won't go into the derivations for these. Just notice that Kf and Kr don't have values assigned to them since not much research has been done on their relationship, so we'll be varying their relationship and seeing the effect it has on our system. Shown here are the reaction equations. In row 1, we see the binding and dissociation of repressor and promoter. Row 2 shows transcription. Row 3 shows translation. Row 4 is the phosphorylation of repressor. Row 5 is the dephosphorylation of it. And rows 6, 7, and 8 respectively show the degradation of phosphorylated repressor, mRNA, and dephosphorylated repressor. So the first thing we'll be taking a look at is the effects of varying Kf and Kr, as mentioned previously. So going from left to right, Kf decreases, Kr increases, and everything else stays the same. So notice how there is no binary switch between the expressions of repressor protein, but rather a relative switch in comparison for each oscillation. As we look from left to right between these three graphs, we see the distance between the peaks and lows of the two curves for every oscillation become increasingly non-ideal and toggle switch behavior decreases. So for optimal toggle switch behavior, we know that the rate of binding of repressor to promoter should be greater than its dissociation, as shown in the graph on the left. And this idea, we'll be using it in all the later simulations. The next thing we'll be taking a look at is how we should be adding the inducer to our system. As the MATLAB code shows here, at every 1,000 seconds, a constant amount of 1 nanomolar of alternating inducer is added. In the legend of the figure shown on the right, the repressors shown with a 1 represent a constant inducer addition of 1 nanomolar, and the 10 shows a constant inducer addition of 10 nanomolar. No matter how much inducer is added, a constant amount is not enough to simulate toggle switch behavior, even if it's 1 nanomolar or 10 nanomolar. So I think the reasoning of this is that a constant amount of competing inducer isn't enough to overcome the large initial peak of repressor seen in the very beginning. So an increasing pattern of inducer must be added, and that's what I show here. I experimented with an exponential pattern of addition, a pattern of 2 to the n shown on the left and 4 to the n on the right. With this pattern, we observe a noticeable difference between the two curves of both graphs at each oscillation peak and low. The 4 to the n pattern shows a greater difference between the two curves. However, this method shows that its proteins reach a negligible value faster than the 2 to the n method and would prove impractical in lab with limited resources. Thus, it seems as though the 2 to the n method shows greater potential for use. Lastly, we'll be manipulating the initial conditions of the system. In all previous simulations, the initial condition has been adding in 1 nanomolar of Aurora A kinase. In this simulation, 1 nanomolar of Aurora A kinase and half a nanomolar of its competing inducer MAP kinase 6 are added to the system, as shown in the MATLAB code on the left. This produces a 2.5-fold decrease in the initial MyB15 peak, as well as a more leveled out distribution of peak repressor expression. This is due to the smaller but noticeable presence of the competing inducer MAP kinase 6 and its ability to control the rise of MyB15 expression. This behavior is preferred to a large initial peak as it would more closely resemble biological systems. In conclusion, this system still requires many improvements, mainly increasing switching threshold and the amount of time that bistableness lasts. There are also a few questions that should be answered before we can make further improvements, such as if the relevant repressors, kinases, or promoters bind specifically to one another, or maybe non-specifically to other things. Overall, this is the first of a few, if any, phosphorylation-only toggle switch systems that allows manipulation of desired protein expression. And here are my references, and thank you for listening.